Hello guys, so let's continue. I think the last we did was we proved why the central angle is twice the angle subtended by the same arc anywhere else, right? So let's get cracking. I also got a feedback that I need to up the pace, and the pace currently is slow. So either you could do two things. I'll try to be faster this time, or you could also run the video at a certain higher speed. Okay, cool. So now we shall continue and look at what could the measure of an angle in the semicircle be. Okay, so let's say we have a minor arc AB. We saw the proof last time that angle APB is half of angle AOB. Right, guys? In this diagram, angle APB is half. If this is x, then this is 2x. Correct? You should also, if you are part of CBSE grade 9 or ICSE grade 10, you need to know the proof. You need to remember how we got there. So just a small reminder for this, you have to join the line OP, correct? And use the fact that the exterior angle is equal to sum of interior opposite angles. It's just a hint or an anchor for you. The minute you do that, if you remember that you have to join and use the exterior angle property, everything else will flow. It is just, it is basic geometry. So if you're in grade 9 or grade 10 and you want to list down all the theorems in this chapter, right? Write down the statement of the theorem, and in some page like a formula sheet, you have a hint or an anchor that will let you have a starting point for the proof of the theorem. So for this central arc theorem, all you need to do is just talk about, write the point exterior angle, and it will help you associate this in your memory, and you could prove it easily. Okay. Now, this is all clear. Moving on, let's say we have a circle and we have a diameter this time. AB is a diameter, okay, which means it passes through the center. And not only that, AB is an arc, right, guys? AB is an arc, and this time AB is neither the major or minor arc because they are equal. The fact that AB is a diameter, arc AB taken this way around, right? Either this way, or the arc AB taken this way around, the measure of arc AB is the same. In this case, if I pick a point on the circumference of the circle, and I call the point R, and if I joined this point to the endpoints of the arc, okay, what could the measure of angle ARB be? What could the measure of this angle be? Now, you know that AB, the diameter is a straight line, so this angle is a 180 degree, right, guys? So going by this, the angle subtended by the arc anywhere else is half of 180, which is a 90 degree, or it is a right angle. Hence, we say that the angle in a semicircle, okay, is 90. It's not only this point, you can pick any other point at random. Okay, if I joined these, you can also construct and try this, guys. Just split a circle into two halves, into two equal parts, and then you pick a point anywhere at random on the circumference. If you join it to the endpoints of the diameter, you will always find that it is 90 degree. Okay, cool. So now if you pick another point this side, okay, let's say this is S. So even angle ASB is going to be a 90. Why is that? Because this time you're looking at 180 degree on the other side. Hence, this is going to be a half of that. Whichever case it is, any angle in a semicircle is a right angle. Guys, this is going to be very, very handy in this chapter. The minute you know there's a semicircle, you can always apply this. Cool? Okay. Moving on. The next theorem, we are going to look at what happens to angles in the same segment, right? Let's remind ourselves what a segment is. let's use the circle out here. If you have a circle, okay, and you have a chord, segment is the area bounded between a chord AB, and its corresponding arc. That is the area that is called a segment. In this case, this is the major segment and this is the minor segment. Correct? Okay. Now, in order to do that, let's go back to what we just learned. Let's say there is an arc DC. Well, DOC is not a quadrant. Let's say it's slightly less than that. Look at the minor arc DC. Minor arc DC. Okay. So if I picked a point that is not on the arc, but it is on the circumference elsewhere, I picked a point A. What could you say about the angle DAC? Okay, you know that this is half of the central angle DOC, right guys? This is what we just proved in the previous video. So DAC is a half of DOC. Supposing I picked another point to B on the circumference, even then this angle DBC is a half of angle DOC. So from 1 and 2, it's obvious that these two angles, DAC and DBC, are in turn equal to one another, right? Now, if we have to state this theorem, right, we can state this in two ways. One is that if you look at the endpoints of the arc DC, we know that the arc in turn contains a chord DC, right? It's obvious. So when you draw this chord, you will realize that this chord splits the circle into a minor and a major segment. And when you look at angle A and angle B here, these two angles belong to the major segment, right? Hence we say angles in the same segment are equal. Okay, this is one way to put this. Another way to talk about the same thing is by saying that the angle subtended by an arc, okay, on the circumference are equal. Because if you look at arc DC, angle DAB and angle DBC are angles subtended by the arc DC, angle subtended by the arc DC on the circumference. So if you're from GCSE or IGCSE curriculum, then you might see this nomenclature used. Okay, angles subtended by the arc DC on the circumference are equal. Okay, if you're from CBSE or ICSE, then this is something you need to be familiar with. It is angles in the same segment are equal. Okay, fantastic. So if you're asked to prove this, guys, and if it's a 4-mark question, then it's better you prove that the central angle is twice the angle in the circumference, and as an outcome, prove this. Okay, otherwise this proof is too small for a 4-mark. Unfortunately, yes, in the Indian syllabus, you have to, based on the volume of the marks allotted to a question, you need to write those many lines. Okay, let's move on. So a way to remember this pictorically, guys, is when you have an arc or a chord, it splits the circle into two parts. These two happen to be the angle in the same segment, APB and AQB. They are equal. Or not only that, even if you consider two random points here and you choose to join them, now you'll realize that, assume these are perfect straight lines like this. Okay, now observe carefully. If I name these points as R and S, then even angle R and S are equal, because this time around, these are the angles subtended by the minor arc, angle subtended by this arc AB, okay, in the minor segment. Right? Therefore, angle ARB will be equal to angle ASB. Either ways, the theorem holds true. Cool. Let's now look at some sums where we apply this. So here's a circle. Now another thing to remember, guys, until and unless a point is mentioned to be the center of the circle, never assume that it's the center. This is something that I've seen most of the students fall prey to. The minute they see chords intersecting somewhere, they say, okay, maybe this is the center, and assume things. Never do that. Always wait for the information given that a point is the center. So right now here we just have two chords. Let me name them A, B, and C, D. And these two chords are intersecting at some point P. Okay. The question asked here is, what is the measure of angle P and measure of angle Q? If you want, pause the video and try and figure it for yourself. Okay. Otherwise, here's how you go about it. If I were to join these points B and D, right? You see that you have chord BD, which splits the circle into two segments, right? Now, with respect to chord BD, when you look at angle BAD and angle BCD, then you realize that these two angles are angles in the same segment. And we know that they are equal. Therefore, the measure of P is 52 degrees. Measure of angle P is 52 degrees. Okay. Another way I ask students to look at is, look here, you have the endpoints are the same, right? BD, you have a B and D. What you're left with is point A and point C. Just, when you have two angles, okay? Or let me state it another way. When you see two angles here, always check where are the other two vertices or endpoints, okay? If they happen to be the same endpoint as this angle, then they are the angles in the same segment. Cool. Similarly, if I were to join AC, oops, it's very, looks like I've drawn another arc here. Just hold on. So if you look at the chord AC, okay, when you look at chord AC, you will realize that this angle Q and this angle 40 degrees is actually angle subtended by the chord AC or angle AC, arc AC on the circumference. So angle ABC is equal to angle ADC. Again, you'll notice here that, look, the endpoints or two vertices of the angle are the same. Then all you need to check is, hey, are the other points on the same segment? If yes, then they are equal. Okay, fantastic. So let's just conclude this. The measure of angle Q is a 40 degree. You have to, guys, always mention the reason. Okay, sometimes until unless it's an multiple choice question or a one marker, you have to provide the reason for how you arrived at the measure of missing angles. Don't forget that. Okay, let's look at this circle, guys. Let's say it's mentioned that O is the center this time. And it is, we are asked to find out angle ACB and angle ADB. We have to find the measure of both these angles, provided we are given the central angle of the arc is a 60 degrees. Central angle of minor arc AB is 60 degrees. Cool. This is very easy. Okay, if you want to pause and try it out. Otherwise, look here, you have ACB is half of AOB. So this is a 30 degrees, right? Now, what about angle ADB? Okay, there are many ways to do this. But for now, observe the fact that we looked at the major arc, okay, or the reflex angle of this arc. If this is 60, if angle AOB is 60, then this reflex angle is going to be a 300 degrees, right? Because angle around about a point is 360. So a reflex AOB is a 360 minus 60, which is 300. Now observe carefully for the major arc AB, so which I'm trying to, just mark it in red. This complete portion is major arc AB, and we have selected a point D, which lies elsewhere, not on the arc, but elsewhere on the circumference. Hence, angle ADB will be a half of the reflex AOB. Right, guys? Therefore, ADB is a half of 300, which is 150. Shall I write this here? 150. Okay. Now, if you just pause and observe, what sort of a shape is ACBD? If I join all these vertices ACBD, I end up with a polygon, right? And this polygon is a 4 vertices, therefore it's a quadrilateral, right? And this quadrilateral is inscribed in a circle, which means all the 4 vertices of this quadrilateral lie on the circumference of the circle. Hence, there's a special name given to this type of a quadrilateral. It's called the cyclic quadrilateral. So when you have a cyclic quadrilateral, right now, this is no proof, this is indeed not a geometrical proof, it's just an observation that the opposite angles of the cyclic quadrilateral, which is angle C and angle D, if you add them up, you get a 180 degrees, which means these two are supplementary angles, right? It's just an observation, but we'll see how we can prove this for any generic cyclic quadrilateral. That's our next theorem. But for now, I thought, we can just look at this particular example. Cool. Moving on. Here's a circle. O is the center of the circle. It's mentioned. We don't have to assume anything. We have an arc AB. We have a point C. Now it's mentioned that this angle COB is a 90 degrees. It's given, and it's given that angle AOC is 120 degrees, okay, or 120 degrees. Now the question is, what is the measure of, find the measure of angle ACB. Okay, that's the first one. And let's also see if there is some way we can find the measure of angle ACO. Okay, we can find many angles here. Why don't we do that? Why don't we write down all the missing angles? Why don't we find angle OAC? Why don't we find angle OCB? Why don't we find angle OBC? Right, guys? Okay. So I would request you to pause the video and try. Otherwise, let's get started. If this is a 90 and this is 120, first and foremost, we are asked to find ACB. How much is this angle? Now, imagine that you're not familiar with any theorem about the circle, but you just know the fact that these 3 are the radii, right? Even with that, you can find this, is it not? You can see that at triangle AOC is isosceles. You can see that triangle BOC is isosceles. So in that way, this is a 45 and this is a 30. right guys? Because if you have this as 30, right, you get a 60 plus 120, which is 180 from missing angle property. So you can say that angle ACB is 75 degrees, or alternatively, you know the fact that this is 120 plus 90 is 210, correct? So this reflex angle, sorry, not the reflex angle, this obtuse angle is going to be a 360 minus 210. Okay, I'm going a little faster here because this basic geometry. So all I mentioned was the reflex AOB is equal to 90 plus 120, correct, which is a 210 degrees. Whereas the obtuse AOB, in this case, the obtuse AOB is going to be a 150, right guys? Now observe, if central angle AOB of this RKB is 150, then angle ACB will be half of the central angle of the minor arc, right? Therefore, even if you follow this line of reasoning, you will still end up with half of 150, which is a 75 degrees. So whichever way, right? It's just that the theorems on circle make it much faster and easier to arrive at the same measure. So that's easy. Now look at ACO, folks. ACO is a 30. We already figured that as part of the isosceles property. OAC is also a 30. OCB is a 45, and OBC is also a 45 degree. Cool, easy, okay. Moving on. Now, this is a question from the CBSE textbook, the NCERT textbook. So here we have a chord BC or an arc BC. No center is given. Can you find out the measure of angle BAC? So the question here is, all this is given. Find, not BAC, why don't we find BDC? Can you do that? Okay, let's find out. If you look at triangle BAC, do you observe that you have the complete angle B? Okay, here guys. And you have the complete angle BCA. So all that you need to do is find the missing angle BAC, right? Which is using the angle sum property. This is 180 minus 69 plus 31, and immediately you will see that this angle BDC is the angle in the same segment. So angle BAC is equal to angle BDC because these are angles, sorry, I need to write neatly, angles in the same segment. Right, so this is another easy one. Moving on, let's look at this diagram. Again, do not assume that BC is the diameter. BC is just a chord. We are to find the measure of, find angle BAC. Okay, we need to find this. Shall we get to that? What are, first and foremost, well, you do see that these two are equal, so just mark them because the angles in the same segment by virtue of the chord BC, correct? Now, how do you proceed? Out here, you see that this angle, right, if I were to mark it like this angle, which is angle CED, and angle BEC are supplementary, or they form a linear pair. They are the angles on the lying on the same straight line. So So they add up to a 180 degree, which means angle CED is going to be 50, right? The minute this is 50 and you have another angle of the same triangle, in this case, we have to look at the triangle ECD. You know, one angle is a 50, you know, the other angle is a 20. So what is the measure of the last angle? Okay, so X or angle EDC is, this is a 70, so it is 110. Am I right, guys? Angle sum property of a triangle gives you EDC as 110, which then helps us to find BAC because these are angles in the same segment. So even BAC is 110, right? EDC and BAC are angles in the same segment. Well, I am just writing it this way. I request you to please write it well with reasons one below the other. I just drop these lines to just show that they are equal. Fantastic.